Okay, so just for fun, for some definition of fun, let's talk about nested radicals and how to denest them. In particular, we're going to look at nested radicals of the form a plus or minus the square root of c, all under a square root, where a and c are integers. We're going to try to rewrite that without the square root on the outside as the sum or difference square root of x plus or minus the square root of y, with x and y integers, or they could possibly be rational. And we're also going to assume that x is greater than y, so that when they are subtracted, we don't get a negative result. Now, possibly you could have a number in front of the square root of c here, and normally what we would do is just bring that inside as a square. Except in one specific case, which makes denesting this form super easy, and that's if the number in front of the square root of c is a 2. If it's a 2 in front, then this problem reduces to a very simple factorization problem. So let me show you with an example. Let's look at the square root of 3 plus 2 square root of 2. And we just want to write this as the sum of the square roots of two integers. And if there is a 2 in front, then this is equivalent to factoring a quadratic expression. All we need to do is find two numbers that multiply to 2 and add to 3. Well, 2 and 1 multiply to 2, and 2 plus 1 is 3. So that's it. This is the square root of 2 plus the square root of 1, or just square root of 2 plus 1. And that's it. So the square root of the quantity 5 plus the square root of 24. Now there's no 2 in front, but we can bring a 2 out if 4 goes into C, in this case 24. And 4 does go to 24, we can bring that 4 out. With 6 left over inside the square root. Now all that we need to find is two numbers that multiply to 6 and add to 5. That's 3 and 2. So this is the square root of 3 plus the square root of 2. Let's look at another one. How about the square root of the quantity 9 minus the square root of 72? First, does 4 go into 72? It looks like it does. 4 times 18 is 72. So let's bring that 4 out of the square root. 9 minus 2 square root of 18. Now there's a minus here, and all that means is that there's a minus between the square root of x and y. We're still looking for two numbers that multiply to 18 that add to 9. 6 and 3 equals 18, and 6 plus 3 equals 9. So 6 and 3 are our two numbers, square root of 6 minus square root of 3. And again, we write the larger number first so that when we subtract, we don't get a negative answer, because we're trying to stick with the principal square root here. Now, for both of these, notice that we could have left that c alone and not factored out a 4 outside of the square root. Take a look at this. 24, there are two numbers that multiply to 24, 6 and 4, that don't add to 5, but they add to 10, which is double 5. Same thing here, two numbers that multiply to 72, 12 and 6, they don't add to 9, but they do add to 18, which is twice 9. That's an interesting thing to notice, because you could have solved these just by finding two numbers that multiply to c and add to twice a. But those two numbers you find, you then have to take half of to get your actual x and y. And in fact, this is how you solve this problem if there is no factor of 2 outside and c is not divisible by 4. For example, square root of the quantity 2 plus the square root of 3. Now you could multiply the top and bottom of this by 2 and then get a common denominator. That works, that can work, but a much quicker way is noticing there's no 2 out front, so let's just find two numbers that multiply to 3. There's only one choice, 3 and 1. And do they add up to double 2? 4? Yes, they do. So our x and y are half of those numbers. Square root of 3 halves plus square root of 1 half. And this is what I mean by certain rational solutions for x and y are okay. Now we could rationalize this too to make it a little bit nicer, multiply the top and bottom of everything by square root of 2, and you would get the square root of 6 plus the square root of 2 all over 2, which is nice. Now notice there is a quick check that will give you a hint whether this will denest or not. And it's kind of like a discriminant, I guess you could say. And that is looking at a squared minus c. If that happens to be a perfect square of some number, whether it's rational or an integer, then we'll be able to find a solution. If it's not a perfect square, we may be out of luck. It doesn't mean there is absolutely no way to denest, but we'd have to do more work. And here's a challenge problem to illustrate that. Here's the square root of 3 plus square root of 12. You can check. A squared minus c is 9 minus 12. That's negative 3. Not only is that not a perfect square, it's not even positive. So that's not looking good for us. However, this still does denest. If you notice that square root of 3 does go into both of these, we could factor that out of both. Square root of 3 plus square root of 12, that equals the square root of square root of 3 times square root of 3 plus square root of 3 times the square root of 4, which of course is 2. Now that's very useful that we're left with the square root of 4 there, because this will allow us to basically switch the roles of the integer part and the square root part. And then we can rewrite that square root of 3 inside the square root as a fourth root of 3 times the square root of 2 plus root 3. And we've already done this one. That's just square root of 6 plus square root of 2 over 2. So it's effectively denested, but with an extra factor of fourth root of 3 over 2. So that discriminant can give us a clue whether this is going to work or not. You just might sometimes get a fancy problem that have a common square root factor that you can factor out and be left with a nice perfect square. So be aware of that weird case. And for a final example, I just want to mention that this also works for complex numbers as well. 3 plus I times 2 square root of 10. Notice there's a 2 in front of the square root. If it was inside, it'd be a square root of 40. This works as well. However, if you bring the I inside the square root, then you notice that this is negative 10 on the inside. So you're trying to find two numbers that multiply to negative 10 and add to 3. And because they multiply to a negative number, you're looking at their difference. Well, 5 and 2 do multiply to 10, and one of them is positive, one of them is negative. Their difference is 3. Their difference is positive 3, so the bigger number is positive. Square root of 5 plus, still plus here, square root of negative 2, which of course is square root of 5 plus I square root of 2. And because the real part here is always going to be positive, this will generally produce the principal square root. But as always with complex numbers, keep track of what branch you're on. Finally, if you've stuck with me this far, you might be curious as to why this works. So let's do a quick overview of the algebraic method of solving this problem. Let's rewrite this. I'm going to use the plus. You could do this with minus as well. You get the same exact result, except with minus here, if there's minus there. And generally, we just square both sides. A plus square root of c equals x plus y plus 2 square root xy. And then we equate like terms. Our integer terms are a equals the sum of x and y, and the square root of c equals 2 square root of xy. Another way of writing this second equation is c equals 4xy. And if you write that as 2x times 2y, then in this case you're looking for two numbers, 2x and 2y, that multiply to c, whose sum is going to be twice a, because x plus y equals a. 2x plus 2y has to be 2a. Now, if we go through the process of solving this system of equations, y equals a minus x, plug that into the other equation, we get c equals 4x times a minus x, c equals 4ax minus 4x squared. Getting everything all to one side, we get 4x squared minus 4ax plus c equals 0. A little bit of quadratic formula and some simplifying, you get x is equal to a plus or minus, but remember x is the larger of these two answers, so I will just say plus square root of a squared minus c. There's our little discriminant there, all over 2. Meanwhile, y is a minus square root of a squared minus c, all over 2. And you can see the solutions, x and y, are only integers, or potentially rationals with a 2 in the denominator, if the thing on the inside of the square root is a nice perfect square. If you like those formulas, you can use those formulas, but I highly recommend practicing the simple factoring method. And after a while, when looking at these kinds of problems, depending on how difficult the numbers are, you could almost do it in your head instantly. But that's enough for now. See you next time.